Okay, so here we are with section 5.6 of the textbook. We sort of take a flyback to Calc 1 and talk about limits again. So now that we know a little bit more about, derivatives of other functions, we're going to sort of elaborate on something that you started Calc 1 with. Now, when you did limits in Calc 1, you didn't know what a derivative was. So there is this other method. So going back over things that you did in Calc 1, when you evaluated limits, the very first thing you did is you did direct substitution, which works on continuous functions, right? So if you just plug in what you're after with your limit, whatever the x value is, if you get an actual number, you're good, you're done, everything's great. If you get some kind of problem, if you get unfortunately, if you were to get an indeterminate form, then you have to try something else. So these are the guys that handle things that don't work via direct substitution. So I'm going to write that word down, indeterminate form. What that means is, from Calc 1, your indeterminate forms were 0 over 0 or infinity over infinity. Nobody can determine what the value of that expression is in that form. There are many different functions and relationships that have that form, but sometimes 0 over 0, for example, would equal 4, and sometimes 0 over 0 equals 1, and sometimes 0 over 0 equals 0. Nobody can determine the answer to that limit just by knowing 0 over 0. You have to do a little bit more investigation. So in Calc 1, you did cancellation, check, rationalization, check, algebraic representations, just do something legal algebraically. What we're going to add to the list, this is the new part, this is new, there it is, new and improved, L'Hopital's rule. There should be a little circumflex here. He's French. So there is L'Hopital's rule. We are going to discuss this. You could not have learned this in Calc 1 because it requires the derivative. And again, you did limits first in Calc 1, then you learned the derivative. So that's why this is a Calc 2 idea. Now you have a lot of different derivative rules under your belt. You can take the derivative of just about any function that somebody throws at you. So now we can handle that last approach, L'Hopital's rule. Now, we could only use it where it's applicable. But let's go through this notation again. Here's our notation of a limit, right? The limit as x approaches a of a function equals L if, L is some real finite number. Okay, so L has to be real and it has to be, finite. Okay, so as x gets really close to a on the x-axis, the y values get really close to L. It does not mean that the value of the function at a is L. That is not necessarily the case. So let me just show you a little quick picture here of sometimes what happens to you in Calc 1. Sometimes you'd have this great graph, and you're doing this analytically, right? But you plug in, let's say, a into the equation. But you don't get an answer. You get one of these weird indeterminate forms, like 0 over 0 or infinity over infinity. There's a hole in the graph. But the limit still exists. There is still a y value that it looks like you're approaching, right? If you approach the graph on the left-hand side, looks like I'm approaching L. And if you approach the graph from the right-hand side, I'm still kind of approaching the same number L from both sides. This limit exists and equals L. It's just that there's no value of the function there. It's a discontinuous function. But remember, we could have a value of a limit even though the function is not continuous. Okay, so L'Hopital's rule is going to come in and oftentimes save the day so that we may not need to do cancellation or rationalization or fancy pants algebra. We can just, if it applies, we can use L'Hopital's rule. So when you look at this, definition of L'Hopital's rule, right? You can apply this to any rational expression so that when you do directly substitute, what all this is saying is if you end up with an indeterminate form of 0 over 0, there it is, you see it, or other indeterminate forms like infinity over infinity, or see how they're putting a negative infinity over infinity, or positive over negative infinity, or two negative infinities over each other. These are all indeterminate forms. So if you produce an indeterminate form of 0 over 0, I'm just going to put like plus minus infinity over infinity, then you can get the green light, as I would say, and you can say, oh, I could just use L'Hopital's rule. That would be great. And you can do that. Okay, so the very first thing you do whenever you're evaluating any limit, I don't care if it's in Calc 1 or Calc 2 or Calc 5 or Advanced Bio or any of these crazy math and science classes, you always start with direct substitution, because if it works by just simply plugging in, then the function is continuous and you're done the problem. So you don't need to make more work for yourself. So if I directly substitute, so I'm going to go ahead and do that. I'm going to switch to blue. I'm going to say, I'm just going to put a ds there. I'm going to directly substitute. This is what you do no matter what. You plug in the 5 for x, that's where this limit is approaching, and you see if you actually get a number. So let's see, that's 25 minus 5. That's 20 minus 6 over 7. That's 14 over 7. That is 2. There is nothing extra needed here. You do not do any fancy methods if they are not required of you. So this is fine. I just plugged in the 5. I got 2. The function is continuous at 5. So it's great. On example 2, when I go to plug in the negative 2, I'm going to do the same thing. I'm going to directly substitute, because 100% of the time, this is your first move on any limit question ever in your life. You're going to plug negative 2 in for x. You're just going to do it. You're going to really be careful with the negative signs here. That is 4 plus 2 minus 6. Now you're in danger zone. I cannot determine the answer to this limit when my punchline is 0 over 0. It doesn't work. I can't do that. What I'm going to have to do is something else. Now, what you can do as your something else is you could go full throttle back to Calc 1 and say, oh, let me see if I can factor that expression. And you'd be absolutely right. This is your old school calculus kicking in. You could factor that polynomial in the numerator. You could realize, hey, I can cancel the top and the bottom, right? Once I get that written correctly. That was a plus 2 in the denominator. That is why I'm slashing it out. It's the same factor in top and bottom. And so you could plug in at this particular stage of the game. And you could say, well, let me just directly substitute into this. You're always trying to get to that moment where you can just plug in. Okay, so my answer here is negative 5. Okay. You could also, if you wanted to, you could change it up and say, I don't want to do factoring. Maybe, you kind of make mistakes factoring. Now you're going to have another option. Okay, so I'm saying this is still on the table. Everything you learn in Calc 1 is certainly valuable and great. At the moment that you got a 0 over 0, what you can do is say, you know what, I'm going to use it. Green light. I'm going to say, this is L'Hopitalable. This is of the form that L'Hopital's rule is permissible. So let's use it. What does that mean? That means take the original limit, and let's go back to what L'Hopital's rule says. It basically says the original limit of that rational expression is going to be equal to the limit of the derivative of the numerator and over the derivative of the denominator. Notice this is not a quotient rule. You are separately taking the derivative of the numerator and the derivative of the denominator and then plugging into that. It's really wild, but it works out. So I'm going to do it. I'm going to say, look, if I L'Hopital this, I just made it a verb, then take the derivative of the numerator, which would be 2x minus 1, take the derivative of the denominator, which is just 1, and now directly substitute. You see what happens here. You end up with the same answer. So this is great. In the introduction to Calc 1, you only had the method in blue. But now that you have L'Hopital's rule, well, this is equally awesome. So it's totally up to you what you would like to do. I'm going to remind you about some of these things over here, example 3 and example 4. And we can do them with L'Hopital's rule if you would like. It doesn't matter. It's whatever you want to do. Okay. So when I think about example 3, I'm going to say, look, I have infinity in this quadratic expression over infinity in this linear expression. Well, this is infinity over infinity. This is a problem. Back to my Calc 1 days, what am I supposed to do with that? Well, this, you could say now, like, that is the indeterminate form that I'm looking for. Indeterminate form. That is your green light to L'Hopital rule this, to say, look, this is going to be exactly the same thing as if I take the derivative of the numerator over the derivative of the denominator and now directly substitute. So I think when you realize plugging infinity into this, right, 2 times infinity, minus 1 doesn't really do anything for you, over 1, this is infinity. It kind of makes, I don't know, it tones it down a little bit. It's up to you how you want to work this out. If you want to see me do it the old Calc 1 way, I don't know, or maybe we get a different Calc 1 instructor. Here's what I would do. Like, definitely I would get the infinity over infinity, but here's the way you probably handle it in Calc 1. You said, look, let's just only pay attention to the biggest power of x in the numerator. So x squared is what's really running the show in that numerator. The minus x is not as important of a term, definitely not the minus 6. When you're talking about plugging in really big numbers like infinity in here, those two don't really do anything. Same thing in the denominator. You just take the biggest power of x and say, you know what, this really behaves like, that original limit behaves like this one, well, which looks like this, which would still give me the same response of, hey, that limit goes to infinity. If I switch these things around, you can kind of say all I did was swap the numerator and denominator for example 4. You can do the same thing. You can say like, hey, Calc 1, this is going to give me infinity over infinity. I don't know what's going on here. How do I decide? That's an indeterminate form. But you can say, hey, this behaves like, let's only pay attention to the most important terms of the numerator and the most important terms of the denominator. And then you can knock it down, and this is a very standard limit that you should know. If you're taking the limit as x goes to infinity of 1 over x, think about it just with numbers, 1/2, 1/10, 1 over 100. This thing is going to 0. And if you don't like this hand-waving technique of like, hey, this behaves like this weird notation that I just decided to use in there, well, then you could absolutely do L'Hopital's rule instead. It definitely fits the conditions here. You have a limit in front of you that works out to be infinity over infinity. That is your green light to, that is an indeterminate form, and that makes L'Hopital's rule applicable. So go ahead and do it. Maybe this is nicer for you. It's up to you. But I can do this as well. And same thing, I have 1 over something going to infinity. It is 0. So you're not going to get a different answer doing it via your old Calc 1 techniques versus L'Hopital's rule. So it's just nice to know that you could do this if you wanted to. Here are some things that you learned back in Calc 1. You learned a lot of your determinant forms. What do you know to be true? Well, we know that if you take infinity and add infinity, you're headed towards infinity. Okay. I know that if I have infinity over some number, like infinity over 5, that's going to infinity. Okay. These are the things you know to be true. 0 to the infinity is 0. 0 to the negative infinity is infinity. Why is that? Well, that's because 0 to the negative infinity is 1 over 0 to the infinity. And if 0 to the infinity is 0, well, remember, 1 over 0 is going to infinity. So that's why that one is the way that it is. And the last one over there is if you have a number like 8 over infinity, that's going to 0. Any kind of static numerator, but your denominator is heading to infinity, well, then your actual value is headed towards 0. Okay. Now, these are the only 2 indeterminate forms that you talked about in Calc 1. 0 over 0. Infinity over infinity. Those are the only ones that work for L'Hopital's rule. But you can see we've got some problem areas here. There are 5 other indeterminate forms that you have to be able to know and recognize. And it's kind of quirky. Indeterminate means, I don't care how smart you are, nobody can determine the answer or the final value based on this form. 0 over 0, like I said, could be 8, could be 2, could be 1/3, could be E. I have no idea. It's a case-by-case issue. Same thing with infinity over infinity. These other guys are problems for different reasons. Infinity minus infinity. Maybe it's 0. Maybe it's not. There are different speeds at which things go to infinity. Some things go to infinity really fast and some things go to infinity really slow, and how they behave with each other. These are problem areas. These are indeterminate. If you get one of these forms, you don't know the answer. If you leave it like this, you're basically saying IDK, like I don't know the answer. You have to be able to investigate further, and it's a case-by-case basis. So these are all indeterminate. These are going to be issues for you. You're going to recognize this form and say, what do I do? You've got to get it into one of these 2 forms for L'Hopital's rule to be your only hope. Like it's the only thing you got. You've got to make sure it looks rational. Okay, so let's get into some of these examples down here. So here I have my first one. And I guess the point here is, I don't want you to L'Hopital things. I don't want you to use L'Hopital's rule if you're not permitted to do so. You have to check the conditions. You have to make sure that it's appropriate to use L'Hopital's rule. So these are the only 2 forms that you are permitted to use L'Hopital's rule for. So look, I'm going to directly substitute and I'm going to see what I get. Every single limit you do for the rest of your life starts with direct substitution. So I'm going to put a little dx, so that's what I'm doing all the time. I'm going to put a 5 wherever the x is. This has to be your first move. You can't say like, oh, look, I see something rational. I'm just going to do L'Hopital's rule. It doesn't work like that. Let's check the conditions first. So when I multiply that out, there's my numerator. There's my denominator. What do I have? 111 over 65. Well, look, that's not indeterminate. That is a determinate value. That is an actual real number L. It's a weird one. 111 over 65. You are done. You do not do L'Hopital's rule on this. You have to get 0 over 0 or infinity over infinity, and I can't stress that enough. So don't just say, it's rational, I'll just use L'Hopital's rule on everything. You will get the wrong answer. You have to check the conditions first. Okay, so I'm done. That's great. That's the best part of direct substitution. So I'm just going to be really obnoxious and write, please, 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 you absolutely cannot use L'Hopital's rule here. It's inappropriate. It will give you the wrong answer. So I want that to be forced and written. The first thing you do is always direct substitution. Okay. Here's our next guy, which is rational. Now again, I am going to directly substitute. And what do I get? E to the 5 times 0 minus 1 over 0. 5 times 0 is 0. E to the 0 is 1. I don't need a calculator for that. This is 0 over 0. So going back to our Calc 1 days, this is a problem for me. This is an indeterminate form. Nobody can tell what the answer is just by knowing it's 0 over 0. That's the whole point of indeterminate. It's not, you're not able to determine the answer. As far as your Calc 1 tricks, you can't factor it. There is no radical to rationalize. I don't have a whole lot of algebra up my sleeve either, so you likely did not see this very often in Calc 1 because it's a little bit more. Maybe you could do a numerical method. I'm not even going to get into that, but we have a way of handling this. Because I have 0 over 0, I'm literally going to switch to green and say, green light, this is something that you can use L'Hopital's rule for. It satisfies the condition, so let's do it. So I'm going to put, hey, this equals the same thing. I'm going to do the derivative of the numerator. Notice I chained that e to the 5x. The derivative of minus 1 is 0, and then the derivative of x is 1. And now you just go to direct substitution, because that's what you do with limits. You do a little bit of work, and then you say, hey, can I plug it in now and get an answer? So I'm going to directly substitute into here. Now remember, e to, let's see, 5 times 0 is 0, so that's e to the 0. E to the 0 is 1. And we're good. My limit is 5. Okay, I don't have a Calc 1 technique to fall back on. You do have a Calc 1 technique for example 7, but I would anticipate not many people remember the little formula, the little trick that was in Calc 1. I'm not even going to mention it because I don't care. Because you have another way around this. You're going to directly substitute with 100% of every limit question you ever get presented to you. So let's directly substitute. Now again, without a calculator, we should be able to do this. We should know that the sign of 0 is in fact 0. And because I'm in this little bit of a pickly situation here, this is an indeterminate form that is 100% legal to use L'Hopital's rule on. So I'm going to put my big green check here. This satisfies the condition. I can use L'Hopital's rule appropriately because I have checked the conditions and I can carry on. Okay, so you can't walk away right now. You're basically saying, I don't know what the answer is. But if I use L'Hopital's rule, I'll take the derivative sign, which is cosine, and then I'll chain it. And then the derivative of 3x is just 3. And so you do it and then you directly substitute. So you've applied L'Hopital's rule. And now you're going to directly substitute and say, let me see if this gets me anywhere. Does this get me an actual value, right? I'm going to put the 4 in front, that coefficient. And then I have times the cosine of 4 times 0. Now, we should be able to know without a calculator that the cosine of 0 is actually 1. So my limit is 4/3. And again, there is an old school Calc 1 technique. I don't need to go over that because L'Hopital's rule saves the day. So, we'll get into some other limit problems here as we motor through these. Okay. Now, again, I can't push this enough. I'm going to keep hammering at this. That if you are presented with a limit question ever in your life, the very first thing everyone is going to do is you're going to directly substitute. Now, some people don't like this, but I'm going to do it anyway. I know what e to the negative x looks like. Here's what I'm going to draw. Here's a graph of e to the x. This is a really good graph to know. Let me pull that down so you can see it. That's what e to the x looks like. E to the negative x, this is like exponential decay. Looks like this. E to the negative x. So if I look at this graph, e to the negative x, and I say, hey, what happens as x goes to infinity? Well, look at your graph. It's going to 0. And then in the denominator, I have 1 plus, and again, e to the negative x as we go to infinity is 0. What is this? That's 0 over 1. 0 over a number is determinately 0. There is no need for L'Hopital's rule. And I say that because I want to make sure you realize if you say, well, I just did L'Hopital's rule anyway, you're going to get the wrong answer. So that's really important. It's not like L'Hopital's rule works everywhere. It only works when you've checked the conditions for those two indeterminate forms. This one it doesn't meet the muster. It does not satisfy the conditions of L'Hopital's rule, but good for me. 0 over 1 is determinately 0, and I am done the problem. Everything's great. I'm going to move on to the next problem. Okay. When I come up to example 10, again, I'm going to directly substitute in here, and that's what you do with every limit you ever see in your life. So what do I have? Negative infinity squared. It's kind of weird to like plug in negative infinity, but essentially that's what I'm kind of doing in my head. And so, negative infinity times negative infinity is just positive infinity. And then remember, e to the negative infinity, if you think about that, sorry for being so graphy here, but what's happening here? There's a couple of ways you can think about it. I can say here's the graph of e to the x. Let's look at as x goes to negative. Let's look at the left-hand side of that graph. You're going to 0. Here's another way you can look at it. It's 1 over e to the infinity. And that should make you feel good. Like 1 over something trucking to infinity is 0. So here we have this, which you did not see in Calculus 1. This is too fancy. Okay, you did not see this in Calculus 1. But here we are in Calculus 2. So this is a problem because that's not an answer. This is an indeterminate form. Problem is, it's a really crummy indeterminate form, meaning I'm not allowed to L'Hopital rule this. There is nothing to L'Hopital rule. There is no rational expression on this function, right? There's nothing rational about that limit. So look, L'Hopital's rule is your only hope. You're going to have to get crafty with this, and you're going to have to create a rational expression. So there is no algebra you can do. There is no cancellation. There is nothing from Calc 1 that you can drag into this problem. But there is something from algebra that you can bring into this problem. Just basic algebra work. I am going to change the way that this looks. I am not going to change the expression, but I need to get something rational. So the easiest thing to do, I know this sounds really crazy, but I'm going to leave the x squared where it is. I'm going to take that e to the x, and I'm going to put it down into the denominator. And when you do that, you can legally do that as long as you change the sign on that exponent to be negative. This is the same expression. This is fancy algebra, right? Like you did a couple of evaluations back in your, fancy advanced algebra class. Like, hey, what's 3 to the negative 2 power? Well, it's 1 over 3 squared. That's 1 over 9. Anytime you change a power from the numerator to denominator, you just change the sign. There I had a negative exponent, made it positive. It works the same way in the other direction. Okay? So I got a little crafty with this. I now have something rational, which is not the green light to use L'Hopital's rule. The green light to use L'Hopital's rule is 0 over 0 or infinity over infinity, end of story. That's your condition. So I'm going to directly substitute and see what happens here. If I plug in negative infinity, well, I would have infinity in the numerator, and I would, e to the negative infinity, e to the infinity, that's infinity. Guess what that is? That is your green light. That is, you move from one indeterminate form to another indeterminate form. But this is a good one because this is your green light to, yep, you absolutely can use L'Hopital's rule on this. So let's go ahead and do it. Derivative of the top, derivative of the bottom. Notice the extra negative is from the chain rule. And I'm going to directly substitute. Oh boy. Well, this is not terrible. I do not have an answer yet. I said yet. This is another indeterminate form. But it's a good indeterminate form because it satisfies the conditions of L'Hopital's rule. You satisfied that. You're allowed to apply L'Hopital's rule as many times as you need to. So I'm going to apply it again. This is like our second iteration, if you want to use that term, of L'Hopital's rule. Keep going until you don't need it anymore. So now what I have here, if I directly substitute, again, all of these cute little methods are just like, do something and then see if you can now plug in. If I plug negative infinity in here, I have 2 over e to the positive infinity. That's 2 over something going to infinity. That is determinately 0. That is my answer. I've answered the question. All this other junk was not answering it. 0, infinity over infinity, negative infinity over negative infinity. Those are not answers. 0 is my answer. And I use L'Hopital's rule twice because it satisfied the conditions twice. Okay. Here we are with example 11. I wish I had put in, well, maybe I will. I'll put parentheses around it maybe before I upload it. Here's our expression. This is a quirky one. And I'm going to directly substitute because that's what you're going to do 100% of the time, anytime you're presented with a limit question. Notice this is a one-sided limit. This is as we approach 1 from the right-hand side. No problem. I'm just going to plug a 1 in. And so natural log of 1 is 0. So 1 over 0 is infinity. Same thing. Plug in 1 a little bit on the right. Here's my issue here. I have infinity minus infinity, which sounds like a good idea. It sounds like it's going to be 0. And it may be 0. I have no idea. But this is not necessarily 0. You can't use logic on this. This is an indeterminate form. Nobody knows the answer when you say, hey, I did a limit and I got infinity minus infinity. This is a case-by-case process that we're going to address. Now, L'Hopital's rule does not apply on this because it does not meet the criteria. It's not 0 over 0 or infinity over infinity. You are going to have to get crafty about reorganizing this limit so that it is one colossal rational expression. This is 2 rational expressions with a minus sign in the middle. So I am just going to use my really good algebra skills and say, oh, I remember this. I remember my crazy algebra teachers. I'm going to switch to blue, where they made me get a common denominator, and everybody hates it. But look, let's legally work on this. This fraction has the natural log of x factor, but is missing the x minus 1. So I'll multiply by it. There's my giant minus sign in the middle. This second fraction has that factor of x minus 1, but is missing the natural log. So do it. You are just changing the way this thing looks. You are not changing this function at all. So I did something. Okay, I'm going to plug in 1 for x because that's what you do with every limit that you ever deal with in your life. So I'm going to directly substitute. And guess what I get? I get 0 over 0. That's awesome. Because that, well, I'm not done. It's an indeterminate form, but that 100% satisfies the conditions of L'Hopital's rule. This is now L'Hopitalable. So what I can do is L'Hopital, again, I'm calling it a verb here. I'm going to use L'Hopital's rule on this limit. So the derivative of x is 1, the derivative of negative 1 is 0, and the derivative of natural log is 1 over x. Now, separate from that, I'm going to do the derivative in the denominator. Now, unfortunately, this is a product rule, so I'm going to do it. First, times the derivative of the second, plus the derivative of the first, times the second unchanged. Now, you just executed L'Hopital's rule. You are now going to directly substitute and see if it produced a determinate answer for you. So when I plug in 1 for x, I end up with 1 minus 1, which is 0. I end up with 1, let's see, I end up with 0 times 1 plus 1 in the denominator. So, did I do that right? Oh, I have a little mistake in here. Let me fix that. Over here. This should be, you guys probably caught me. This should be an x minus 1. So when I do my direct substitution, natural log of 1 is 0, and there's my 1. Here, 1 over 1 is 1, and then 1 minus 1 is 0. So unfortunately, I still have 0 over 0, which is still indeterminate. However, it's still legal to use L'Hopital's rule. So because I am still within the conditions of L'Hopital's rule, we're going to do L'Hopital's rule again. Let's see, the derivative of 1 is 0. That's already a 0. The derivative of negative 1 over x, let's see, that's negative x to the negative 1. So that's going to be positive x to the negative 2. And I'll do the derivative down there. The derivative of the natural log of x is just 1 over x. Pull that up so we can see that. And now over here, I need to product rule this. So I needed to go first times the derivative of the second plus the derivative of that times the second unchanged. And I am going to directly substitute that. Let's see, 1 to the negative 2 is 1. In the denominator down here, I have 1 plus 1 plus 0. That was a lot of work. But I finally got a determinant answer. My answer is 1/2. That was a lot. I started out with an indeterminate form. I had to get it into a better L'Hopitalable form. I had to use L'Hopital's rule twice. I had to use the product rule in order to do these derivatives. That's certainly a fancy one. Okay. Let's go over to the very last problem from this section of the textbook here, which you can kind of see this theme rolling through a lot of things. This is our last example here. This is interesting. You see you have a variable base and a variable exponent. So, all right, let's get into it. You are going to directly substitute, and when I directly substitute this, what I end up with is 1 to the infinity. That is a problem. I know you want to say the answer is 1. Unfortunately, this is also one of those indeterminate forms. There are 5 other indeterminate forms that you need to know. You need to memorize them. Okay. So here we have an indeterminate form. This is an indeterminate form that is not L'Hopitalable. You cannot use L'Hopital's rule in the form that it is in right now. What I'm going to do is use a familiar technique that we've been talking about over the last couple of notes here. I am going to say, if only I had a logarithm in this problem, in this limit. If I just had a little ln in there, this would be amazing. So let's make it happen. All right, let's set this equal to y. I'm going to say, look, this limit, I'm going to say it's y. The reason I'm going to do that is so I can actually take the natural log of both sides. So we're going to now put that little logarithm, that natural log, right in front of this crazy exponential where you have x in the base and in the power. So there's what I have. The answer to this question is going to be, I need to find y. I need to keep my eye on the prize here. I need to find what the value of y is. I'm going to keep that in the back of my mind. I need to find out what y equals. Now, I have to deal with what I have here. Now, the good news is, because you introduced that natural log, what is permissible on this right-hand side is using the properties of logarithms. Drop that 1 over x in front of the natural log. Do it. It's great. If I directly substitute over here on the right, I end up with an equally terrifying result. I end up getting, if I directly substitute right here, I end up getting infinity times 0, which, if you're paying attention, is another indeterminate form. It's better than the one we started with. Nobody knows the answer, but I cannot use L'Hopital's rule yet. What I need to do is force this expression to be rational. I need this to be rational. And it doesn't take as much craftiness as it did in the last problem. It kind of is rational. I really just have the natural log function and x is in the denominator. That's a legal way to write that expression. And let's directly substitute here. When I plug in 0 for x, I get 0 over 0. This is exciting. You are not done. But you are now at a legal indeterminate form to say, yes, I am permitted to use L'Hopital's rule, and I will do that. Okay? So you're using L'Hopital's rule on the right-hand side. And remember, when you use L'Hopital's rule, you're not doing the quotient rule. It's actually better, right? You're just saying, hey, what's the derivative of the numerator? Well, the derivative of the natural log is 1 over what was inside. And then the derivative of x is just 1. If I directly substitute 0 in for x, I get 1. Now, I need you to be really careful. That is not the answer to our question. Remember, there's a natural log of y. That's just kind of carrying through this process. Remember I said keep your eye on the prize. Your eye on this prize is, what is the value of y? The natural log of y is 1. You need to solve that equation and get what y is. You need to go back to your pre-cal days. How do you solve a logarithmic equation? You exponentiate. E up against the natural log cancels that out. What that means is y is e. So to answer this question here, you were looking for what y is. What this means is, and I'll switch to blue so it's easier to see, the limit as x approaches 0 on the right of this function is e. That's tricky, because you did all this work and you get 1. And then you have to realize, wait, but that's natural log of y. Let me actually solve that out, and let me get to my finish line. And you've arrived.